Thank you. So hi everyone, it's great to be here at PyCon Czechia. Today we're going to be talking about some challenges that data-intensive applications face at scale and how some probabilistic techniques can actually help tame those problems. Before introducing myself, I will encourage you to point your phones at this QR code because you might want to save the slides for later. They contain references, they contain like more details that I'm going to go into today. Maybe if they spark your curiosity, you can learn more about this stuff. So again, I'm Alberto from Venice, Italy. I've been working for around 8 years as a software engineer. I'm also a consultant. And what brings me here to Prague is my collaboration with the Czech Technical University. We're working on like some data modeling, pipelines, mathematical optimization problems with Python. But actually, most of the time, I work with other languages like Rust and TypeScript. My background is mostly on like database toolings, both for standard SQL-style databases and for full-text search at Prisma and Orama. Actually, today we're going to take some of the problems and solutions that stem from internals of databases, popular databases, and we're going to see how they can help reducing the memory load of your modern applications. So our goal for today is find new ways of lowering this memory footprint of your databases or like your real-time streams. We're going to look at how to compress the representation of your input in such a way that you can still be able to formulate queries. They might not be as precise as before, but you can really tune and configure how precise you want them to be. And we will also develop the intuition behind like some mathematical properties that allow you to have these probabilistic data structures and tools in the first place. So let's start with an example. I believe you're familiar with a similar logo. Imagine a social network for your pets, like your favorite animals, cats, dogs. You may like photos of them, you may do all of the things. And of course, since we don't have that much creativity, we're going to call that petgram. So how many features does this social network support? Well, you can post pictures, you can post videos of your animals, you can have live streams of a cat fighting with something on the table and putting that, of course, he will win the battle. You can search for hashtags like chunky, fluffy, whatever adjective you can imagine. You can like, comment, you imagine you have like tens of thousands of likes in some viral posts, and you can even save things for later. So just like any social network, you're mostly concerned about keeping track of everything that the user do. Like, you're really poking at all the data you can find from the users. Like, how many times do they interact with something? How many times they interact with each other? Which kind of topics they like the most? So you're going to have like raw data coming in your system. And at scale, you can have like terabytes or petabytes of them every day. It doesn't come in a nicely formatted table, as you see here. It mostly comes in like key value pieces. You just receive them, and then you are supposed to elaborate on them and aggregate those results, those data on the fly. And why are you supposed to aggregate things as fast as possible? Because users in modern applications expect fast feedback. Whenever you see a viral post or a viral tweet, for instance, you don't let's say that it was posted 5 minutes ago, and you see it has 100 likes. And if you keep your application open for 1 minute there, you don't expect it the counter to remain at 100 likes. You expect it to go up as you look at it, because it's viral. It's not 2005 anymore. We have WebSockets and other things, right? The problem is that it's very hard to keep up with an accurate count of interactions, because you will have to go through all the previous data several times for millions of users. That just doesn't scale. So sometimes we need alternatives. We want to analyze data in real time, but we want also real-time performance. Users and product managers alike may start asking questions about the features that the product offers, right? So for instance, let's say there is a viral live stream. A user will probably want to know how many views, how many unique views the live stream has had. Like how many unique users have I impacted with this live stream of my cat. And the traditional approach is computing a distinct count SQL query. And similarly, if you are developing a recommender system, you probably don't want to show the same post to the user more than once. So you might want to ask yourself, has this user already seen the post? And how can you determine that? Traditionally, with a select exists query. Again, these queries, in the traditional sense, they need to go through all the historical data for that user, and then use maybe indexes to filter down on only the data for the user. But they might not really scale much. And there are some problems to keep in mind. Like the most interesting questions we may ask are so-called non-additive. What this means is that you can't just take a large amount of data, partition that into chunks, process them all in parallel, compute local results, and then aggregate them back together. Because what you will get is something different than the result of the operation you would expect. Like sorting has this problem, counting unique things has this problem. Like you find a unique entry in one element, in one set, and in the other, then chances are you can have the same unique element both here and there. So if you put the two sets together, you no longer have a unique element in the join set. And another thing to consider is that when you have so many storage options, like so much data to store, you want to really avoid moving that data across different storage devices. Because every time you go from disk to memory, to RAM, from RAM to CPU cache, etc., you pay a price. So ideally, for this sort of real-time computations, you would like to keep all in memory. And that's a problem when you have like terabytes. That's a problem when you consider that RAM costs much more than SSDs and hard disks. But that's something to keep in mind. And another thing is, at some point, if we start optimizing for space, so if we start minimizing the space we need, we also minimize the time we need to compute the answers for the queries that we need. And do we even need exact answers? Like, if I'm seeing a video of a live stream and it has 10,000 views, or at least it tells me it has 10,000 views, but in truth it has 10,005, is my user experience really that impacted? Or is somebody else, if a user already liked the post and he sees the post twice because the recommender system somehow failed to recognize that, is the user that pissed off? Sometimes yes, but not necessarily. So the thing to understand here is that sometimes it's fair and it's okay to estimate things as long as we're close enough. And we can estimate things right now, get them fast, get them cheap, and still provide a nice user experience. And then over time, we can refine them. We can make them more precise, kind of like YouTube does with the video counts. So we can start to accept some inaccuracy. Of course, we don't want unbounded inaccuracy, right? We want to be sure that our answer to the query is still precise enough, it's still close enough. So we want a predictable level. And one of the best tools for this, or at least like one of the principal tools for this, is hash-based sketches. And they are like probabilistic data structures, and they have this very nice feature in which they don't need your data. They don't need to store your data to actually allow you to ask questions about the data itself. So they just need to see your data once, maybe processing that in a stream. And processing things in streams requires much less memory than keep everything in memory persistently. So that's quite neat. And in particular, they have like a few nice features. Well, you can consider them as a summary of your data set. And your data set might be something in a time window of all the events that come into your login system. You have specialized sketches depending on the type of queries that you might need. So if you want to know like how frequently a video was liked, or how many unique users have that, you're going to have a different type of sketches to use under the hood. Most importantly, they are sublinear in space. So if you have, I don't know, terabytes of data, once you summarize them with sketches, you actually end up with gigabytes. They have like mathematical proving guarantees. We're gonna just give the intuition for them. And the tools we introduced today are Bloom filters and count min sketches. And they are all based on hash functions. So a little bit of our review on hash functions, probably are all already familiar with them, but what's important is that they are deterministic. They take an input that can be any value of any kind, as long as they have like the __ hash function in Python, and they compute a value out of it, usually a big number. The important caveat is that the input set is significantly larger than the output set most of the time. What this means is that you could take like consider every possible computable string, and you can actually summarize that by applying the hash function into a range of int16 numbers, or int32 numbers, or whatever. And of course, by the pigeon principle, if the codomain of the function is smaller than the domain, you necessarily have some collisions. Like you have some, you apply the hash function to different inputs, and in some cases, you might get the same value. And this creates some problem. And another thing to consider is that we want hash functions to be like uniformly distributed, because otherwise the mathematical guarantees of probabilistic data structures don't really hold. The good thing is that there are plenty of good hash functions out there. Let's see also a little bit of a categorization. Usually there are like cryptographic hash functions for cybersecurity purposes. We don't need them. They are very good, but they take too much to compute, and we want very fast results. We want to compute hash functions in constant time. And thankfully, there are also like very great tools and frameworks providing non-cryptographic hash functions like Murmur3, and that's what we're gonna focus on. The primary data structure you probably already know that uses hash functions are hash tables. And if you paid attention, hash tables can actually, like you could solve the queries we've seen before with hash tables only. What are the problem? Their problem is that they require, like they're very fast, like every operation is insertion, deletion, lookup. It's constant time with some amortization, but they take linear space in terms of the data that they have to contain. They have to keep track of every key and value pairs you found into like their own buckets, but they have to store them to retrieve them. And that's the problem. They store the entire data set. If you need to process terabytes, they need to store terabytes. And it's not feasible unless you go into, split the hash tables into pages, kind of like the memory system, the operating system does. It becomes quite tricky very soon. And the simplest probabilistic data structure we'll see are Bloom filters. They don't have anything to do with flowers. It's just the name of the author that created them in the 70s. And you can think of them as a compact representation of a set with n distinct values. And what's important is that you have to think a priori how many values that set is going to contain. So you need to have some sort of estimate of how many elements you're going to witness. They support insertions, they support deletions. Unfortunately, they don't support, they support insertions and lookups, but they don't support deletions by default. And the type of queries they answer are membership queries. The kind of, does element X belong to set A? Like, does this kind of, the idea is that you need to, you want to identify whether an element has already appeared in the past, like you've already seen a post in your feed, but without keeping track of everything that was in your feed before. And how you do that? Well, you store everything in a bit set. And the bit set has a size proportional to the number of elements that you expect to see. So we can also already see that the space we need is no longer dependent on how many elements we actually get, and no longer dependent on how large those elements are, right? Because sometimes you might hash values that are 1 megabyte each, if they are like large objects, and sometimes you hash and actually we just need a few bits per each element that we want to keep track of. And there are a few use cases. Well, popular databases or like data processing tools, Apache Cassandra, Kafka, and others, they use Bloom filters under the hood. And they were also used in the past for like determining, as you typed your password in a login system, whether your password was safe or whether it was already leaked in some online database. And how do they work? First of all, you have like two primary inputs. The number of bits of the bit set, right? And the more you have, the more precise your data structure is going to be. And the number of hash functions you want to apply. And the core idea is that if you have different hash functions and you apply them, you get a position in the bit set, right? You just apply a modulo operation with them, and you get the range from 0 to m-1. Well, you can start storing things into the bit set by spreading them out into multiple positions. And by spreading them out, you limit the chance of having hash collisions. And how do they work? Well, first of all, we apply the k-distinct hash functions to an input value. We get the positions in the bit set, and then the bit set is initialized to 0, and of course it's a bit, so it can only be 0 and 1. And if the position selected, any value is set to 0, we actually turn it on, turn the bit on, so we set it to 1. And when we perform the lookup, we get a probabilistic answer, like, does element X belong to the set A? We answer no if at least one of the bits selected is set to 0, and we answer yes, maybe, if everyone is set to 1. And that's where the probability comes in, because this yes could actually present false positives. Chances are it's going to be the correct answer, but in a small percentage of cases, it's going to be the wrong answer. And it's probably much easier to see an example. So here we have 8 bits. So we're basically spending 1 byte per each element we want to keep track of. 2 different hash functions with k equals 2, and we have this very nice bit set initialized to 0. We get the first element x, and we apply the k different hash functions. We get positions 1 and 2. So position 1 and 2, right? The bits are set to 0, so we increment them. We set them to 1. We activate them. And the same goes for another element like y. We get values 2 and 4. At position 2 and 4, we take whatever was before and we replace that with 1. So that's what we are left with after inserting 2 elements. You see, we are only flipped 3 bits. Because of course, some of the hash functions, they gave us the same values. What happens when we perform lookups? Like, have we actually seen value x before? So we kind of repeat the same process. We apply a hash function twice. We get position 1 and 4 because the hash functions are the same as before. And we see that every selected value in yellow is set to 1. So the Bloom filter says, yes, we found it. And in this case, we get a true positive because we already inserted that before, we know that. But what about element z? Our Bloom filter has never seen element z. If we apply the hash functions, we have position 1 and 2. It just so happens that position 1 and 2 are selected in red. They are also with active bits. But that's the wrong answer. Like we say, yes, we found it, but we didn't. We didn't insert that before, so that's a false positive. In terms of complexity, well, that's pretty much the same as hash tables. The number of hash functions you use is generally so small that can be considered as constant, and the space is only determined by the number of bits, plus how many hash functions you want to store in your data structure. And a little bit of glimpse about notation, please don't get scared about the mathematical parts of it. The important thing to remember is that your false positive rate, which is the frequency with which you get a wrong answer, strictly correlates with the number of elements that you plan on having and the number of hash functions you use. The more hash functions you apply, the safer your results are going to be, like the more realistic your answers are going to be. But also, the smaller the number of bits you select, then the larger the chance that you get a wrong answer. And there's like a degenerate case when the m bits are all set. Remember, we never remove elements. We always keep adding them, so at some point that could happen. Then every lookup you perform yields a positive answer. That's the degenerate case. And that's why you need to estimate the number of elements you want to store up front, so you can plan for it. You can also tune that. You can find like the optimal k and m value with some mathematical formulas. This is just an example where we see that if we use a Bloom filter and we allow 2% of the time to get the wrong answer, then we can just use 1 gigabyte rather than using a hash table that will require us to store 24 gigabytes. So we already see a 24x improvement. And other benchmarks you can perform, these results can grow higher, like 64 or 68 better than hash tables. And a few takeaways about this, before moving on to the structure, is that they are great, Bloom filters are great for space-constrained membership queries, so you can answer, does this element belong to the set, with very little storage consumption. Caveat is that you can't really delete things, so at some point you have to kind of create a new Bloom filter from scratch from the next time window of a stream you get to your database. But there are other Bloom filters evolutions, like cuckoo filters, quadrant filters, they support deletions. And they also can be resized, just like your general vector or hash tables are resized if the number of the number of elements you insert surpasses the initial expectations. They mostly perform well on uniform databases, on uniform distributions. On non-uniform cases, sometimes they don't work that well, and you still get alternatives for them, like weighted Bloom filters. Quickly, count-bin sketches, they are pretty much Bloom filters, all stacked on top of each other, and they answer frequency queries, like how often does this element appear in this multiset? And a multiset is just a set where you get a frequency value for each element. And again, they don't store anything, the dataset itself, and they have a table like k rows and m columns, where k, again, is the number of hash functions. Where would you use them? Again, Apache Cassandra, Apache Flink, some databases. You can use them, like Twitter uses them to determine which are the most trending hashtags, because they are like the top k hashtags. And how do they work? Well, you still have the k-distinct hash functions, right? The idea is that each hash functions controls one row of a counting table, and then you first, it's probably just easier to see that in practice, right? Just to make sure we are on time. So we see 8 counters in this case. That's the number of elements, the number of columns. We have 3 rows. That's the number of hash functions. Again, we want hash functions to be independent, and we want the initial matrix to be 0 initialized. We start adding an element. In this case, it's an update operation. What does it mean? We say that element x now occurs 2 times, additional 2 times than before. And what do? We perform the hash values, and we see 2, 5, 0. So hash number 0 controls the first row, so the row 0. And we go to the second element here, and we add the frequency that we got in the update operation here. So we see that +2. Hash function 1, we get 5, so the row at the index at 1, position 5, we increment by 2, and so on. We repeat the process for another element y, and again for another element z. So we are left with this matrix here. No longer bits, they are just counters, they are just int 32 or something. Now what happens when we perform estimates? Now the cool part about count-min is that they perform the minimum, they take the minimum out of the possible estimates. And they do so that they never underestimate your count. They can overestimate but never underestimate. So what happens in this case? We have Z, we apply, we see that at row 0, we need to get second position. Row 1, first position. row to 0th position. We take that 5, 3, and 5, we compute the minimum, that is 3, and that's the correct estimate, because before, we said that the frequency of z was 3. And what happens if we try to estimate x? Well, we repeat the process, 5, 3, and 5, and we get an overestimate, because x was, I believe it was 2. And again, complexity is the same, literally the same as Bloom filters. In principle, you just have to multiply the, like every Bloom filter you stack on top of each other. So you have m times k factor in the space. They are much more complex to reason about error, like the probability of an error appearing. I'm just gonna leave this as a kind of detail for you to check up later. Basically, you can determine what's the frequency of you getting an error and how much do you get an error, how large that error is in terms of the sum of all frequencies. You can tune them, you can get the optimal k and m values for it, and the takeaways is that you can apply them for these frequency queries. They might be a little bit biased. So if you apply, if you take the estimation on average, they will be always a little bit overestimated in terms of the actual count of your frequency. There are alternatives like count median. I'm just going to leave it for later. Very quickly, how could we implement them? Well, the interface is, as you see, just a constructor you insert and look up for Bloom filters. And you have a hash function that you will reuse. And the hash function is parameterized because we have h0, h1, and h2. We will use bit arrays. So we just store the input elements and the estimate of how many items you want to store, and the number of bits you want to have in your bit set, and k, the number of hash functions. And we initialize the bit array, which is m, which has an m size, to 0. Now, about the hash functions, we can use the Murmur hash, as we've seen before, non-cryptographic, deterministic. And we just apply the sit so that we get, mm3 hash of a value, comma 0 would be different than mm3 hash value, comma 1. So that's a great part of that. We don't need different families of hash functions. Then we just apply the modulo operation to the size of the bit set. And that will give us a position within the bit set range. And for insertion, we repeat the same operation for k times. We first get an index of the bit set by applying the hash function with the e variable as a SID. And then we mark the presence. How do we mark the presence? We just set the bit to 1. About lookups, again, we repeat the same operation k times. We keep searching for the position in the bit set. And we know that if we find a 0, if we encounter 0, then it's definitely, the element is definitely not present. It didn't appear in the dataset before. Otherwise, if everything is set to 1, we agree that the value likely appeared in the dataset before. So we return yes. What about count min sketches? Very similar API. In this case, we have updates, and they kind of incremented the frequency, and estimates as lookups. Similarly, we get k and m. We no longer need n this time. We initialize the metrics. We have k rows, and we have m columns. So it's essentially Bloom filters stuck on top of each other, where rather than using bits, you use normal number arrays. Again, the hash functions is exactly the same. The implementation is exactly the same. For performing updates, again, k times you perform an operation. You select the column by applying the hi hash function, or h row, in this case, hash function. And then you select the position at the row and column and just increment it by the count you were given as an input. And to estimate, this is a little bit more interesting. I'm using lazy generated lists. Probably there was a talk this morning about that. But very briefly, this is like the context of your estimates. This is like an unrealized list, so it doesn't consume that much memory when you compute that. how to read that? For every row in the K range, and row would be like the iterate of your hash function, we first of all select the column, then we select the estimate, which is just the value in the matrix at the column and row position. Then we return the estimate. And we select the latest element of this list via this -1 at the end. And we just compute the minimum after that. We compute the minimum and we return it as as the answer of how many times did value appear in the dataset from before. This could be an overestimation. So hopefully now you will no longer consider probabilistic data structures as magic, even though they kind of feel like that. So thanks so much for having me. Here you also have some resources for you later to learn more about them. And thanks for PyCon and for every one of you for your attention.
Thank you so much. I have 2 short questions here, so let's get straight to them. Is this available in any standard querying tool, or do we need to implement it ourselves? Maybe in Spark, which allows approximate count distinct? Vojta asks.
So partially Spark, I know that they ship with probabilistic data structures. They have some collections for that. I don't remember the name precisely, but also if you use Redis, an in-memory data store, which is very fast and powerful, and is perfectly capable of doing this kind of queries, you do have a module for probabilistic data structures, and they are very fine-tuned, they are more precise, they are more powerful than the ones I've shown today, but they are still based on count sketches and Bloom filters.
Okay, one more question. Can we guarantee robustness of Bloom filters against adversarial examples, where an attacker wants to induce a high number of false positives?
So like the easiest way of inducing a huge number of false positives is if you spam the event system too much, more than they expect. So they will quickly fill up the available bits you set before. And that's why you want Bloom filters that can grow over time to kind of compensate for that, which do exist. Another problem is, which is not really adversarial, but you could probably find what hash function, with enough patience, what hash function your system is using, or like the system you're attacking is using. If you find that, and if you find exploits for those hash functions, so that you can arbitrarily cause conflicts, then the more conflicts you can create, the more false positives you're going to get. And in that case, yeah, you could probably perform an adversarial attack. I believe there are researches in this area, like you find papers from computer science institutes that approach this problem.